be on storage systems. So next talk is on hard drive for low power, energy efficiency in disk storage system by Sridhar Chatradhi from Hitachi. And there he is, so Sridhar.
Good morning. Can you hear me? Yes. Okay, my name is Sridhar Chatradhi, and I work for Hitachi Global Storage Technologies. It used to be the IBM hard disk drive division merged with Hitachi. I would like to first thank Jeff and Eli and UC Berkeley for giving me this opportunity. And I also want to thank Jim Donaldson sitting there, my colleague, and Zvonimir Bandik, who contributed towards this. I'm an optimist. So I believe that if we put enough human energy into solving this energy consumption reduction problem, we can do it. I don't care whether we do it through mechanical relays or nanomagnetics or whatever. I think there's enough energy here, enough brain power, it will be done. So my talk is about the disk drive systems. And in our industry, we have been spinning disks for 5 decades. Billions of disks there, right? IBM invented RAMAC, the first disk drive in 1956. And it was a breakthrough technology at that time. It stored about 5 megabytes in 50 24-inch disks. Nobody at that time cared about power, though, I think. One of the websites I looked at, the data from IBM showed it consumed about 52 kVA. And this is not including the cooling that was required, the big cooling towers for, anyway, the mainframes and the big storage systems. We worked very hard. The latest disk drive in 2008, 1 terabyte drive, idle power about 5.2 watts. So, I mean, good progress there, but always a lot to be done. So we are in the 4th era of HDDs. So the first era was the mainframe era, and then the mini computer, and then the PC era. You see the growth there in, this is the button, I think.
Button on
top, right. Sorry. You see how the digital storage requirements have grown with so many devices using disk drives now, like set-top boxes, game stations, DVRs, whatever. So the storage requirements are growing exponentially, and we are trying to reduce power. At the same time, we are doubling storage every generation. So it's an interesting problem for us to keep the watts per gigabyte low. This, again, data from IDC and our own estimates of disk storage. If I had shown this chart 1 year back, it was going 10% CAGR. Because of recession, there's a dip there in 2009. And I mean, it's bad news for us selling disk drives, but overall, for power consumption, maybe it's okay. Google CEO said, what matters most to the computer designers at Google is not speed, but power, low power, because data centers can consume as much electricity as a city. Data centers have become the poster child or favorite whipping boy for power. That's because they're more visible. There's large concentration of computing power and storage in one room, and you can see the cooling requirements and all the heat dissipated there. But it's, as Jonathan earlier mentioned, it's not without reason. They do consume a lot of energy. According to EPA report, In 2006, they consumed about 61 billion kilowatt hours of energy, electricity. And the bad news is it's likely to double by 2011. Right? If you look at the hard disk drives, according to 2008 IDC report, the total cost of an HDD in power is 48 watts. 12 watts for running the HDD, 12 watts for storage shelves, and 24 watts to cool the HDDs and storage shelves. Okay, so when we are making HDD, it's not just the power that is dissipated in the HDD, but overall power required in the data center. So as I said, the gigabytes per watt is very important. When they did RAMAC, power probably was not a big concern. The trend started more recently to focus on saving power in the disk drive. And if we plot the last 3 generations in our enterprise class SAS drives, the 3.5-inch drives, you can see the annual energy cost for petabyte go from 300,000 to less than 100,000. This is taking into account all the cooling requirements and the HDD power in a data center. Right? So, I mean, we're looking at power usage effectiveness now in data centers, which is total facility power divided by the computing equipment power to measure the efficiency of data center. So, in a 2.5-inch drive, one generation, if we focus on power, for the same amount of capacity growth, the cost reduction is this much. If we don't focus on power, just increase the capacity, we would be there. So focus on power is important while we focus on increasing the capacity. So in a hard disk drive, why saving power is important? I mean, apart from being good for the environment, it makes economic sense. It saves money on power supplies, cooling, cost of powering the HDD, and most importantly, it increases the reliability. There is a direct correlation between the temperature the drive is running at and its reliability. And the temperature, as the temperature increases, there's a big drop in reliability as the drive ages in the second year or third year. Right? So longer HDD life means less frequent replacement of HDDs, so it saves money. Apart from that, there are, of course, Energy Star and other programs emphasizing product efficiency, and there are standards coming from initiatives from industry like Green Grid and Climate Savers Computing. And another important part is low power is becoming increasingly a part of bids from the government and several big accounts like Google. Okay, I said it makes economic sense for us. So we like to say we are doing this for the environment, but our customers also push us into low power because it makes economic sense, right? The customers are asking for lower RPM hard disk drives in storage systems. Earlier, it used to be how much performance can you give? What is the access time of the disk drive, right? So let's bump up the RPM. Well, now for tier 2 or tier 3 storage, well, even if it runs at a little lower RPM, it saves power and it's not affecting the performance that much of the overall system. So, advanced power management features, standards. I have a slide on that later, but in SAS drives, like Bruce was saying yesterday, the thinking is we need the device to be on all the time, right? Available. So the SAS interface was waiting to receive commands anytime, and most of the time it is sitting idle. Whereas SATA devices, because of battery life in laptops, the standards bodies have come up with power saving modes a lot earlier than SAS, and now it's coming up in SAS. There's a shift from using 3.5-inch large form factor drives to 2.5-inch form factor drives. The power density increases. You're packing more in a smaller area, but overall power reduces because the disk diameter is going down. In the consumer electronics area, low RPM drives, the focus there is not only on power, but acoustics and reliability. Desktop PC, Energy Star specifications are making an impact there. And there is also a trend towards moving into 2.5-inch compact systems. And notebook computing, as you know, battery life is very important to all of us, right? Okay, what are the specs that influence power in HDDs? Lower RPM means lower power. So for example, on the same capacity drive, if you reduce the RPM from 7200 to 5400 on a desktop drive, we can save about 2 to 3 watts of power. And in a desktop environment, the performance difference probably is not that significant if power is important there. Diameter of platters. As I earlier mentioned, if you go from 3.5-inch to 2.5-inch, there's significant power reduction because the actuator need not move that much, and spinning smaller disks takes lesser power. Number of platters. Fewer platters, lower power. And of course, performance. Higher performance requires higher power. If you want to seek very fast, it requires more energy. But we cannot have everything, right? So there has to be a trade-off between capacity, performance requirements, and power based on applications. So in a disk drive, there are 2 major components. The mechanical power, you have the platters, the spindle motor, the head stack assembly, and the voltage coil motor for moving the actuator. We need power to run the spindle motor, power to move actuator, and most of it is 12 volts today. Not in the laptops though, but in enterprise and desktop. In the electronics, it's basically power to run all the major chips there, and it's mostly derived from 5 volts. So we talked about standby power, sleep power yesterday. In a laptop drive, there are so many different modes, power modes that are maintained. So if you look at a spinning up of the drive, it takes 5 watts peak. The others are average power. So when you're seeking, it's about 2.5 watts. Read write continuously, it's about little over 1.5 watts. But you see the amount of savings when the drive is in sleep mode or standby mode. Okay, what are the different power reduction efforts we put into the disk drives? In electronics, it's the silicon technology and design improvements we've been talking about since yesterday. We try to do all those clock gating, low power design techniques, and all that to save power. Adaptive voltage schemes, frequency reduction in low power modes, improving power regulator efficiency. In firmware, this is where it gets more interesting. There are so many different benchmarks we support. And it's very hard to collect data on the access patterns. It varies with different applications. So there are several queuing algorithms that are implemented to optimize the rotational position and the delays accessing the data. And also some good algorithms to manage the transition between different power modes based on time or activity patterns, whatever. In the servomechanical area, of course, lighter materials for moving parts consume less power, but we cannot make them too light that they don't have enough strength. Less air drag on actuator and disk. A lot of our efforts go into combating this air drag in lowering the 12-volt power. Some of the ideas there that are being in the works now are hermetically sealed drives filled with helium, and efficient motor design, algorithms to lower energy per seek. I have a slide on just-in-time seek, how that is used, and use of load-unload during low power modes. Load-unload. Prior to using this technology, in fact, some drives still use this contact start-stop technology where when the disk is not rotating, the head rests on the disk, right? So when the disk and the head area, they're very smooth, there is stiction. So it requires a lot more power to take it off. Also, you cannot have too many modes. If you want to not move the actuator, you have to stop spinning and rest the actuator on the disk. So when you have to access data again, you have to spin up, it takes a lot more power. With this load-unload technology, there is a small ramp where this actuator can go and rest while the disk is spinning and can move quickly when data needs to be accessed. So you'll get more options to manage different power modes with this kind of technology. It also increases the number of start-stop cycles for low power applications. You don't need to have this stiction problem, and it improves reliability. Just-in-time seek. When a request for data comes to the disk drive, the actuator might be in some position. We seek to go to the right track and then wait for the starting LBA, starting block there, the target block, and then start the transfer, right? Now, you can go very fast and land on the track and wait for the rotational delay for the target block to arrive, or you can predict how long it would take to get there right at the time when your target block is close to the actuator, and either seek very slowly with low velocity and low power, or you can use that time to improve performance and seek fast later, right? So just-in-time seek saves significant amount of power. In fact, I think it's about 2 watts or something like that. So there's a lot of intelligence into these algorithms to predict the estimated seek times based on several parameters. Adaptive battery life extender. IBM started this technology in 1991. It's one of the first attempts at saving power on disk drives. Okay. In general, in the industry, there were 4 power modes at that time: active, idle, standby, sleep. If you look at the amount of energy it requires to spin up drive, that's much more than if the drive is running and you just have to move the actuator. So transitioning into these modes, we have to make sure that the energy that we are saving by going into the sleep mode is more than the energy we spend to spin up the disk. So by having a lot more power modes available, and by implementing algorithms that transition between these modes with a finer control, we can save more power. And this is a table that shows what part of the disk drive is on or off, and how much power we can save in each of these modes. So say, for example, from a read-write active mode, which takes about 1.8 watts in a laptop drive, a 2.5-inch drive, to about 0.1 watts in sleep mode. Right? Here, most of everything is off. Like the spindle is not moving anymore. Efficient regulators. Traditionally, in disk drives, linear regulators were used, and as you know, we get about 50% power efficiency on those. We switched to switching regulators, and it made a big difference in overall power. Now, of course, we are using a combination of synchronous, asynchronous switching regulators to save power. Okay, power management standards. In SATA, we have active, idle, standby, and sleep mode defined in the standards. So active is when the drive is fully powered up. Idle, it is capable of responding to commands. It takes a little longer time, but drive is still spinning. Standby, drive is spun down, and it can take about 30 seconds to respond to commands. And sleep is the lowest power mode. It takes 30 seconds to power up, and it will receive a reset. That means the drive is, electronics is loading code again from the disk drive and getting ready to do the transfers. In SATA specification for the PHY, the serializer deserializer interface on the at the physical layer, there are 3 modes: PHY ready, partial, and slumber mode. So in partial mode, the drive has to wake up and respond in 10 microseconds, whereas in slumber mode, it can take 10 milliseconds. So the host can send a command to put it in either partial or full slumber mode based on the access patterns. And a device that implements these power management standards should support a standby timer and be able to check power mode command, support the command, and support all these other modes. In SAS, similar efforts are going on in the committees. T10 committee is discussing several proposals, and it's at a stage when the I think standard would be approved anytime now. There are several more modes in the SAS standard that are coming up: active, idle A, B, C, standby Y, and Z. The standard doesn't specify what exactly should be done in each of these modes. It's up to the disk drive vendors, but eventually some consensus would emerge in the industry. Again, in the SAS, they have partial slumber and other modes. In disk drives, the system level efficiency is very important to understand the characteristics of the drive. So efficient management requires knowing the when to go into low power modes and all that. There are so many initiatives made and others that are being used. They can do a lot of capacity and data management, like techniques like compression to reduce the amount of storage requirement, tiered storage with tier 1, 0 with solid state drives, tier 1 with high performance, and 2 with power HDDs and data deduplication. There are other system level examples like audio visual storage manager, which is an application that if there are multiple movie streams running on a drive, this application intelligently reduces the duty cycle to the drive by sequencing the commands. So, and you can see the amount of power saved when we do that. If there are, say, 8 movies running, you can save about 1.2 watts of power per HDD. So this is a simple system level application that we developed, and it can be installed and it saves power, right? I mean, you don't need hardware changes or anything for something like this. So there are several such ideas to save power. And to summarize, disk storage is a significant portion of data center energy consumption. We all know that and are aware of that. And continued growth is expected. There are industry-wide efforts to reduce power consumption. Standardization is key to achieving system-level efficiencies. And system-level power management solutions are very important to get overall energy efficiency. Thank you. Any questions?
Thank you, Sridhar. There's room for questions.
Yeah, I can yell on.
It's easier that way.
Hi, there's much talk about power management and turning disk drives off in particular, that it affects MBTF adversely. Basically, the disks last longer and failure rates go up. Is that true, and to what extent is that pronounced, and how does this various power-saving state transitions affect MTBF one way or the other?
It is true. There are a certain number of load-unload cycles that a disk drive supports or specifies for a given MTBF. You can't spin down and spin up, infinitely. So there is an impact on that, and in fact, there is an effort in the standards bodies to change the commands. I mean, when the command comes into, say, go into a low power mode, if we run out of the quota for the day or for the month of number of load unload cycles, what do we do? So that issue is still not resolved.
Is there any work on making multi-RPM type disk drives so that you can do something like DVFS?
In some of the modes, we go to lower RPMs. That is being done. But when you say multi-RPM...
Like sometimes I want to be running at 15K, sometimes I want to be running at 5400 when I'm retrieving data.
That is possible. It's not in the disk drives implemented yet. But in low power modes, we do have a low RPM mode.
And is anything being done to make disk drives spin up and down much more quickly? Because part of the problem with disk drives is, unlike solid state, you can't do in microseconds turn them on and off. So are you doing something to make it sort of sub-second spin up and spin down?
Sub-second is tough, but we do work continuously to improve that. There are mechanical limitations to that.
Just follow up on the comment about solid-state drives. Does Hitachi make solid-state drives, and can you compare the cost and storage capacity and power consumption for a solid-state drive?
Yes, we announced a partnership with Intel in enterprise-level solid-state drives. The power consumption there, again, depends on the technology, whether we're using MLC, SLC, and the capacity of the drive. The big advantage is in idle power. It's very low compared to the enterprise storage disk drive. Operating power, again, it's not that lower compared to a disk drive. Cost is there's big difference in per gigabyte cost.
So I was just curious, this data might have been somewhere sort of buried in the slides, but if you looked at sort of a typical usage scenario, can you comment a little bit about just where's the power distributed between the different components? Like, is it, mostly the servo or the electronics, or just in general, where's the power mostly being spent?
Again, depends on what activity we are doing at that time. The mechanical power is more in the spindle motor and the actuator. In fact, there's about 40 to 50% of the power for the mechanical moving the actuator and spindle during active. In fact, during spin up, it is much more. As we go into low power modes, we are not moving the actuator. We are spinning the drive at lower RPM, or even spinning it down. Then the electronics power stays there, unless we turn off the entire clocks. Right. So, yeah, 60% mechanical power, 40% electronics power, depending on the activity we're doing.
All right, I think I'm